When you're holding in your hands something like this high quality binocular, you should be aware that you're holding in your hand a piece of modern marvel, a true miracle. If you think about it, the optical engineer, the mechanical engineer, the product designer, the director of sales, the director of marketing, the accounting department, the purchasing department, the head of the assembly line, all of these guys came together and had a meeting, not just one meeting, a series of meetings. And not only were they able to come out alive without scratches and with the correct number of eyes and ears and fingers, but they were able to bring to market a product that provides good quality, good value for a customer, good enough for people to open their wallets and part with their money and go and enjoy this. And therefore the price of such quality instruments is very high. This particular binocular was sold in its day for almost $3,000 in that neighborhood. Now you may ask, and the customer is 100% justified and in fact even encouraged to ask this question, okay, fine, so you manage not to murder each other, you manage to have some meetings and come to an agreement and come out with a product, why do I need to pay for that, and why so much? And of course the simple answer is that all of this is expensive, and apparently that is the only way to accomplish this, right? If someone else was able to offer a product of similar quality at a lower price, they would do it. So unfortunately, this is the price that we need to pay for the materials, the manufacturing, all of the expertise and the knowledge that comes with it, the fiscal risk, and so on and so forth. And to really understand this from a more global perspective, or if you will, I'm not a fan of using buzzwords and fashionable buzzwords, but I think in this case it is warranted. So one of the current buzzwords is holistic. Everything needs to be holistic. What does that mean? It means to take a more encompassing perspective, to examine the components of something and not just looking at it, let's just say, with a camera lens from the photographer's perspective, or with a binocular not only from a birder or a hunter's perspective, but to get a better idea of the greater picture. So the materials, manufacturing, like I mentioned before. So just like the previous video, we're going to switch to the slide now, and again, apologies for the change in audio quality, but again, the audio quality for the slides is better, so I hope that that's going to be better. You're not going to have all the noise. And so let's dive into it. Let's talk a little bit about the industry in general, the glass industry, manufacturing, and then towards the end we are going to go into optical, not so much theoretical principles like in the previous video, but more practical terminology, and how does that work, and how does it really influence, and how it is related, or how it is relevant to these instruments and how we use it. So let's talk about standards and specifications and things of that nature. Let's switch to the slides now. Here we are, and we're going to start with talking about glass. And before we continue, I just want to reiterate that the purpose of this video is just giving you a little bit better understanding of the entire picture of glass manufacturing, optics manufacturing, how it works, and to dispel a lot of notions. There's a lot of bad stuff, bad so-called information, or erroneous information based on incomplete or mistaken knowledge, and it would be worthwhile to dispel those notions. So what is glass? Of course, it's the primary component of optics. Let's not forget that the glass is not just suspended in thin air, but it has to be in housing, and it has to be properly built and properly positioned within the optic. But nonetheless, people talk about glass all the time, glass quality, which again is understandable because it is important and it is the primary component of optics. So what is glass? It is a non-crystalline substance which is primarily based on silica, which is a fancy word for sand. It has to be mixed with other chemicals. Everything has to be extremely pure and very carefully crafted. It requires a lot of expertise, experience, knowledge. And here is where what I mentioned before, the so-called or quote unquote holistic approach. There is a lot of things that you don't normally think about that go into this. There is negotiating deals, there is choosing vendors, getting the deliveries, storage, retrieval, all of that. If you want to do it good, it's expensive. You have to have a good team, a good employees who are conscientious, who know what they're doing, who want to do the right thing. So it's just endless. That there is a lot of bookkeeping and a lot of accounting and a lot of economics that go into this. Someone has to figure out why go to one vendor versus another. Sometimes you must go with one vendor because you buy 5 things from him or 6 things from him, and you can't buy a seventh from a different vendor. So there's always a myriad of things that go in the background that we don't see. Now, again, the manufacturing of glass is a super, super difficult and tedious process that requires a ton of expertise. So all of these chemicals, they're finally bought. So now we have to know what kind of glass we're manufacturing. And we're going to go into this a little bit later. Now we decide how much we need. And that's pretty limited. We can't just do any quantity of glass. The glass shaping vessel, the glass casting receptacle, is a certain size. You can't put less, you can't put more in most cases. So that's already a limitation, deciding on the schedule, on what glass to pour, how much to pour. Making it is super, super tedious. You have to warm it up a certain way. You have to go from this temperature to the next temperature in a certain amount of time. From then the next step, it's another set of time, and so on and so forth. Same thing with cooling. Now we have a huge ball of glass. We have to break it in order to break it down to smaller components. So it never ends. Bottom line, it's expensive and tedious. And yes, technology advances, it becomes always more efficient. There's always better processes. People come up with better ways and more economic ways to manufacture glass. But in principle, it is still a difficult and tedious process, at least high quality optical glass. And the vast majority of truly super high quantity glass, like I said, doesn't go to sport and consumer optics. It doesn't go into binoculars and camera lenses. It goes to the semiconductor manufacturing industry, it goes to the medical industry, to the aerospace defense industry, and so on. So the tolerances are extremely exacting. Very, very little deviance is allowable. The density, the clarity of the optical glass must remain consistent throughout the entire batch. So when you break it up, it has to be the same thing almost everywhere, right? Once the big ball of glass is broken down, almost each big piece will go to a specific industry. The tolerances are measured sometimes in a fraction of a green wave of light, so nanometers, very small. Again, the idea is to maximize light throughput and minimize all adverse effects, all what is called artifacts, meaning defects or distortions. Need a high level of precision. And then, of course, the glass manufacturer typically sells what's called blanks to optical manufacturers, and blanks can be in different stages. It can already be a certain diameter of cut lenses or a rod from which lenses can be cut. Today, optical manufacturers already start shaping the lens very often, so it's a growing trend already for the past couple of years. And in other words, that the brand that will make the finished good or the sub-assembly, the component, will get already pre-shaped lenses, and they're going to finish putting the exact prescription and then the coating. And the coating of the lenses is a whole other rigmarole. It's a whole other song and dance. But coatings are also super, super tiny and fine, and the process to adhere the coating to the lenses is also very, very tedious. And then, of course, grinding, polishing, cleaning, coating the lenses is expensive and tedious. So I guess by this time you get the picture. Now let's talk a little bit about industry terms and definitions. What is just jargon? What is marketing hype? What is semi not very transparent or not very honest terminology? The first meaning of the word standard is something that is standardized and that has legal repercussions. And this typical weight and measures are standardized. A pound has to be a pound anywhere. A bushel has to be a bushel, an inch, a foot, a mile, a yard, and so on and so forth. Weight, volume, other things such as heat, throughput, so emission of heat, light, and so on, a candle and a lumen. If you buy a light bulb in the store and it says a certain amount of lumens, it has to mean something, right? So if a supermarket orders 100 bushels of apples, and then all of a sudden the DoorDash delivery guy comes out with a tiny little bag and it says, here, our bushels are smaller. No, you can't do that. That's illegal, and that's why there are standard institutes. And of course, this is just the simple things. Many, many other things are standardized, as we shall see, different kinds of metals, different materials. So it's much more vast than this. Now, a specification is now based on standards, and it tells us what we want, what details we want. So we can specify something in weight, in material, in length, in volume, and so forth. And then there is tolerant, is the amount of permissible deviation from the specification. So if I say that I want to manufacture a chair that has a seat of 14 by 14 inches, and then the manufacturer delivers me chairs that can be 14.1 or 14.2 inches, that might be within tolerance. So at the time of signing the contract, I want to say how much tolerance I'm willing to accept, and they can say what is their industry capability. They can go down to, let's just say, a tenth of an inch or a hundredth of an inch, and of course, the more exacting the tolerance, the more expensive the process will be. And now let's go back to standard, which is a secondary meaning, and that is a set of performance requirements. So I want an automobile to perform on a certain level, or something even simpler. A flashlight, it has to emit X amount of light, it has to consume the battery in X amount of time, so not to consume the battery faster than that or sooner than that. Water resistance, so ingest protection, all of these are standardized. Case in point, the military around the late 90s underwent a fairly big de-bureaucratization process, and they simplified a lot of things. So until then, a lot of military products or military products that were being purchased by the military had very, very exacting specifications, and they were very anal, and they were mostly concentrating on inches and ounces and pounds. So everything was very, very precisely described. So a certain rifle had to have a certain length of a barrel and made of a certain material, and so on and so forth. And then slowly they started to realize that it's more important to concentrate on performance. And in principle, you couldn't care less if the rifle is made out of toilet paper if it performs properly. Of course, this is an exaggeration, but the idea is that not to concentrate so much on the small details, on how many inches and how many ounces and pounds and what is the exact material it has to be made from, but mostly performance, which of course includes durability as well. So there was a shift in mentality, and that shift, of course, went to the military, not by itself, but it came from the civilian market, which is typically always much faster to go in these directions. But of course, in the civilian market, it happened over a much longer swath of time, and it was over many different parts of many industries. Now let's talk a little bit materials, because glass is a material, and there are a lot of lores and legends regarding glass. Um, One of the preferred marketing terms of the automobile industry is alloy. Alloy. This gives you an alloy wheel, and an alloy this, and an alloy that. Well, guess what? Every metal that you come in contact with in day-to-day life is an alloy. So when the automobile industry tells you that they has alloy wheels, it just means that it's a fancier alloy, it's a nicer. But regular steel that you encounter every day, even regular iron, if you were come in contact with, is really wrought iron. It's carbonized iron. It's just cold iron. But the actual element that's pure iron or pure aluminum, that doesn't exist in the practical world. You can buy it maybe in a laboratory. You can go to a high school teacher supply store and buy pure metal, pure aluminum, or pure gold, or whatever, and you could see that it doesn't hold together. You can squash it with your hand. It crumbles. So all metals are being alloyed for industry, for practical purposes, for everyday use. And how they alloy it and what they alloy them with, the primary component is usually carbon. But then they are categorized into different series, right? So aluminum, the series 2000, 6000, 7000, which is generalized as aerospace industry aluminum. There are, of course, many more series of aluminum, and if they give you a certain code, 6065 or 7075 or 6061, that pertains to the exact makeup of that kind of aluminum. Now, why are there so many different kinds of aluminum? Obviously, for different purposes. Some aluminum needs to be easily machined and cheap, and so it has less rigorous requirements. Some aluminum has more rigorous requirements. It has to be more resistant, more resilient to shock, to bending, to corrosion, and so on and so forth. So the military typically will use 6000 and 7000 series aluminum for AR-based weapons and so on and so forth. And the T means heat treatment. So there's T5 or T6 or T4 and so on and so forth. And that is all described how to perform that heat treatment once the metal is formed. The same thing with steel. So there is 4041, which is a very popular carbon steel. There is 304, which is a kind of stainless steel. 316 is another kind of stainless steel. And all of this is being standardized by a standard institute. In the United States, it's the SAE, the Automobile Standards Industry, the Institute, the Automobile Standards Institute that standardizes metals. So case in point, you cannot make the claim that a 316 stainless steel is inherently better than 304. It has different requirements. Same thing with aluminum. 7075 is not inherently better than 6061 or 6065. It's just that it has different requirements. That's number one. Number two, and this is the biggie, the Standard Institute just tells you the component, how many percent steel. So I'm just making up, but let's just say 304 has to have 91% iron, and the rest of the 88 other percent is some carbon, between 1 and 2, maybe 3% carbon, and then it has molybdenum and chrome and nickel and God knows what else. So if there is a manufacturer that manufactures high quality and they do all the processes properly and they don't take shortcuts and they don't hire stupid employees and they know what they're doing and they care what they're doing, they will give you a high quality bar stock 304. If you buy from a vendor that is cheap and they say this is our 304 aluminum, but they take shortcuts, they don't heat it properly, they don't cool it properly, they don't cut it properly, they don't load it properly, they don't store it properly, you're going to get an inferior product. So again, the case in point, and this is going to be the underlying recurring theme in this video, that numbers themselves don't mean much. Okay, so even if no one cheated you and actually delivered you the product that you ordered, be it 316 stainless steel or 7075 aluminum, it doesn't really matter because what's more important than that is the actual quality of the product being delivered, and of course, ditto for all product across practically most industries whenever it really does matter. So the glass also, someone can tell you that they're selling you X, Y, and Z type of glass or kind of glass, and soon we're going to go into that as you can see on the slide. But it doesn't. It's no testimony to the actual quality of the glass itself. Now, glass is classified in different ways. So there are just general terms such as crown glass and flint glass. Flint is simply a little bit harder glass, and crown is typically glass that goes on the outer parts of an optical of a simple optical system. Again, in very general terms, but it doesn't have a very precise meaning. Now, then there are glass internal codes. So BK and BAK. These codes, they denote something very specific, borosilicate crown, and it gets even more specific than this, as we shall see. But the mere notion of or the names BK and BAK, these belong to a certain glass manufacturer. So if you want to make the same glass, you're not allowed to call it BAK. You can call it something similar, but you cannot copy this. These are actually trademarks that belong to one specific glass maker. Now, because it is the most famous or the most well-known glass maker, the entire industry uses this as a baseline, if you will. So they will compare their product to this, or they would offer a similar product, but they cannot sell it as BK or BAK. So BK just means borosilicate crown, which is a fairly precise term, and BAK means barium crown, and as you can already imagine, it's based on the component. F is a relatively new kind of glass, a couple decades
or so. And
Fluoride, contrary to popular belief, doesn't have any kind of magical powers or inherently superior optical performance or attributes that make the glass better. Simply, in the mid or late 90s, the ROHS, which is the European counterpart of the American EPA, they said that the glass industry should not use lead anymore because it goes back into the environment and can be harmful. Now, obviously, people don't go out on camping and hunting and hiking in order to break their expensive binoculars. And even if on a rare occasion it does happen, it is not so tragic. It's not such a big deal. The big deal, of course, is manufacturing because all of these industrial residues, they're very often harmful, sometimes even poisonous. There's all kinds of other chemicals. And so that's why lead has been outlawed to protect the environment, at least that's what they claim. And the optical industry, for the most part, has replaced it with fluoride in most instances. That's all. But fluoride glass is not inherently better. It's just a newer fad. And a couple of years back, people used to make a huge, big deal about it. Now, the glass code, that is something very, very specific, and that is standardized, and that is has to adhere to certain standards. So when someone sells you a certain glass code, they must sell you that. But again, like I said before, that is not necessarily a testimony to the quality of that glass. The glass code is made up of 6 digits. The first 3 digits are denoting the refractive index, and the second, the Abbe number, which is defined such as a capital V and a regular lowercase d. And the manufacturer code, each manufacturer having their own trademarked code. And we quantify glass by several attributes. The density, which has a big influence on the index of refraction, the Abbe number, which is the diffraction, that is the index of dispersion. So typically you want the first three to be as high as possible and the second three as low as possible, again, given the requirements and the context and the condition. Now, tolerance for imperfections or artifacts, as we call them, for scratch, dig, crush, rub, bubble, striations, leaks, all of these things have to be given. Now, again, these tolerances are already not included in the glass code. you don't know this. This is something that the glass manufacturer does not divulge to you, the customer, in most cases, unless maybe if you ask for it, they may tell you. The consistency of the substance, if there are, it's impossible to make it 100% perfect, but the distance between imperfections, so how many imperfections and of what kind are permitted in a millimeter cube per glass or centimeter cube, however they measure that. Now, once the glass is complete, the specific product can be manufactured. So, like I said, they break down the glass, and then based on what it's intended for, they can further shape it. And today, the manufacturer sometimes goes down as precisely as to even put in the prescription, or at least the rough shape of the product. Let's take now a typical page of a glass manufacturer catalog. So this one is actually a Hoya, no, I'm sorry, it's an O'Hara catalog, and they show you for comparison all of their competitors. So this is Schott, which is kind of the gold standard of the industry. They're from Jena, Germany, which is and then was for a very long time, since the 19th century, the glass capital of the world. Not just optical glass, but decorative or utilitarian glass like plates and glasses. And then you have the other big Japanese manufacturers, Hoya, Hikari, and there are some more. I think Corning is now, they're doing something super specific. So they exited the market general. I think they only do medical or something like that. But anyway, so as you can see, this is something objective. This is something concrete, and it means something. So the refractive index, the three main digits are 439, and then the index of diffraction is 948, and it just happened to be backwards, but it doesn't matter. Now, if you look good, you can see that it says here BK7 and then BAK2. These are fair. Okay, this used to be BAK4, but in this case it's BAK2, but it could be also BAK4. So the N just denotes the newer designation or the newer cataloging system, which happened, I don't know what year, 2000 and something. But it's in principle it's the same thing as BK7. So if you want to make a glass, you're not allowed to sell it as BK7. I don't exactly know under what law or agreement they're allowed this for comparison, but they're not misleading the customer. So the customer is looking at here, they know that they're dealing with O'Hara, they're buying stuff from O'Hara, but they know that this is comparable to Schott's BK7. A while ago, BK7 was getting a bad rap versus BAK4. Someone made a big deal and said that prisms must be out of BAK4, but BK7 prisms are worthless, which is totally untrue. BAK4 simply has a higher index of refraction. As you can see, again, like I said, this is a BAK2, but technically it could be a BAK4 as well, which is relatively similar. So it has a 540 index of refraction, and this only has a 516. And again, the actual index of refraction goes much more. So there is a decimal, and these are the numbers after the decimal, but it's not like the fourth or fifth are irrelevant. But for cataloging purposes, we use the first three after the decimal. So be it as it may, if you build a poro binocular with prisms made out of BK7 and you look under certain conditions and low light, you can see like a frame, like a little black lines that make it look a little bit squarish. So it's not as good. So it's true that it's better to make a poro binocular with BAK4, but again, it's not like BK7 is an inferior product. It's a different product with a lower index of refraction. So this is pretty much what we need to know, and it's important to understand that the industry is bound by certain rules and regulations, and they always try to bypass that and play games and tricks on you. So a utility patent protects tangibles such as machines. So let's take, for example, an engine. Let's just say Dodge's Hemi engine, right? So that was patented for a duration of 20 years. No one's allowed to copy and make an identical engine. Even if they sell it under a different name, they can say that this is now Johnny's engine or whatever the name is. Now the copyright
that protects an intellectual property, such as a book or a song. You wrote a book or you composed a song, people are not allowed to sell it as them. This is a little bit less relevant to here because we're dealing more with trademarks. So trademark is something like a logo or the name of a company, right? The big famous names. So someone is not allowed to sell another product that says Coca-Cola on it or things of that nature. Someone's not allowed to copy the Mercedes logo, right, the emblem, and sell their product under that. So the case in point, back to the example of Hemi engine, no one's allowed to use the word Hemi on their engine, even if it's a different engine. So after 20 years, the utility patent expires, and you're allowed to copy the same exact engine down to the tiniest component, make an exact replica, an exact copy, and you can sell it. But you must not sell it as Hemi, because then you're misleading the customer, which leads me to be careful of what manufacturers tell you and how they market things to you. Sometimes people misuse these terms. People say that, let's just say, cameras come standard with a strap or with a cleaning kit. Well, guess what? They don't. That's an industry practice. It's best practices. It pays to give the customer like a little something cheap to make him happy, so that they don't have to run and buy a separate strap and a separate cleaning kit. But it's not a standard, right? But we kind of misuse that term. Or very often, optics retailers or optic brands will say that, oh, this optic has 90% transmission or 95 or 92, whatever the case is. Well, guess what? There is no such thing as light transmission. As we shall see a little bit further on, the proper term is throughput, and even that is not all that precise. But again, light transmission is not 100% straight, not 100% honest with the customer. Again, what I just said here, and this is very important, and it goes into the price, and that's what I said in the very beginning, that every single step of the industry and bringing a product to market can be very tedious, and there are many pitfalls. There is another little notion, a misconception that someone started a while ago on the big internet forums, and they said that really all manufacturers make the same optics because there's only a handful, 4 or maybe 5 different kinds of optical prescription software. So that part is true. Yes, there might just be a few softwares to calculate prescriptions in optical lenses. That's very true. But remember, the software doesn't go to cut and grind and polish those lenses. So who employs that software, how they employ it, how they implement it is extremely, extremely influential and crucial in producing the final product. Imagine saying that I don't know what, there is an accounting firm, and well, all they use is an Excel sheet to put in your gains and your losses and to calculate your taxes, right? And so why should I go to the expensive accounting firm when I can just take Johnny from the corner? He uses the same Excel sheet. Well, that's stupid. Just because they use the same software doesn't mean that the outcome is going to be the same. So it's pretty much similar. Now let's see what the optical industry produces. One of usually the lowest or easiest part or component is a mirror. Mirrors reflect light, like we've seen in the first video, rather than refract, and they typically converge, although they can be divergent as well. And they used to focus light, so they used a lot in telescopes and a lot of medical instruments, and sometimes they are used in outdoors optics, like spottingscopes or binoculars, especially in wartime, and typically those are polished metal mirrors. And of course, in cameras and some medical equipments, there are mirrors. The image attitude correction system is typically based on prisms, and that's very popular in sport optics. Like I said, in binoculars and spotting scopes, there's almost invariably prisms. Riflescopes typically don't employ prisms; they rely on a lens system. That's why they're so long. There's several types of prisms. There is the big distinction is Poro and Dach, or roof prism. Dach in the Schmidt type. Dach is the most popular today because it's the most compact, and until not very long ago, it was still relatively complicated and expensive to manufacture. But again, like I said, efficiency is always increasing, and the coating the prisms and cutting the prisms is becoming easier and easier. So there's less and less Poro prisms. From time to time, here and there, you see an Abe-Koenig type prism, which is kind of also long, but it's still inline, not like the Poro prism. And both the Dach kinds require phase coating, but the Poro doesn't need any kind of coating. That's one of the big advantages of the Poro prism. And the Abe-Koenig type requires only a phase coating, whereas the Schmidt also requires a dielectric mirror coating in order to render a proper image. The attributes of a typical lens is the type, meaning the shape, the prescription, the power, not to be confused with what we say in colloquial jargon, power for telescopes or binoculars. Power here, this is the light bending power, and it depends on the density of the glass, of course, and the radius of curvature, the thickness of the lens, the F number. Now, again, the F number doesn't depend on a single lens. A single lens is typically a component, but certain lenses lend themselves to be in an X range of focal lengths, typically in very simple and simplified terms. And again, the index of refraction is in the glass itself, but very often is also given for a specific lens. And as you can see here, there are many different shapes of lenses for many different purposes. And in a camera lens, for example, this is how they would be arranged. So those that are cemented together are called a group, and the lenses could be air-spaced. As you can see here, this is a very typical air-spaced objective, and there is another airspace here. This denotes the diaphragm, the adjustable aperture that can be found in camera lenses. And this is a cemented group, and this is another group with three lenses that are air-spaced. So this is what is called a certain amount of lenses in certain amount of elements in certain amount of groups. So that's very big, especially with camera lenses. Let's talk a little bit about distortions or imperfections. And this is the most famous one, chromatic aberration. And I want to remind you that this is only a two-dimensional representation of a three-dimensional phenomenon or three-dimensional environment. So this happens in all 360 degrees, right, round and round. But representing it on paper would be super difficult and disturbing, and we wouldn't get the idea. But as a side note, it's somewhat unfortunate that we live in a world where we absorb most of our knowledge in a two-dimensional way. So we live in a three-dimensional world. We walk, we go up and down, we move in three dimensions, but the absorption of information and knowledge happens on just two dimensions most of the time. You open a book, those who still have paper books, God forbid, but you read from left to right and then the lines from top to bottom. So again, two-dimensional. You look on the screen, everything is two-dimensional, and then you force your brain in sort of a mold that is two-dimensional instead of thinking in multiple dimensions. If you think even of something as simple as an Excel sheet, which is an example I typically give, we should be able to arrange those different tabs one behind the other and kind of look through and train our brains to think that way. But okay, rant over. This is just kind of a side remark. Anyway, looking from the side on a cutaway diagram, what happens is that each color is a different, you remember from the first video, a different wavelength. And since each wavelength travels a little bit differently, once we break or redirect the light, refract it, it will focus, it will fall on a different point. So this is very easy to understand from this diagram. So if we go from left to right, we have the blue and then the green and then the red. And of course, the end result to the viewer is that some of the image is not focused properly. Whatever is in the red spectrum, let's just say that this is our focal plane. Everything that's in the red spectrum will look good, but whatever is greenish and bluish will look out of focus, and that is called chromatic aberration. Just a quick remark here. In optics, almost all imperfections or aberrations or distortions are due to spatial problems. So as you can see, this is a spatial problem. This is not an inherently color problem. Well, of course, the wavelength of the color, but this is a space problem. So they're not being projected on the same exact focal plane. But what is perceived as a problem with color, we call it an aberration. What is perceived as a problem with shape, we express it as a distortion. So we can talk about barrel distortion or pincushion distortion that distorts the appearance of shapes of objects. So straight lines become curved inwards or outwards. There's no problem with the color. So but the cause is typically spatial in most cases. So what do we do to fix this problem? Where here there is a crown, which is a softer glass, but higher bending power than to a lens made out of flint glass, and also it's a different shape. So this is you remember what the name was from here? So it looks like it does. Oh, here, a biconvex, and then we have a plano concave. Just turn the other direction, and these two are cemented, but they don't necessarily have to be. And what happens here is that almost all the colors are focused almost exactly on the same plane. Now it's possible to make an even bigger correction that is approaching 100%, even though it's not 100% perfect, but to most eyes it will look in most cases perfect, and then adding another element or higher quality element, so we can perfect the system a little bit further. Let's take a look at prisms. This is how a simple polar prism works, and this is an excellent representation because it makes it so simple and so evident. And as you can see, we have an object here, and this is not in honor of the F word. It's simply very easy to understand and to see which way it is being oriented. So if it's upside down and flipped the wrong side, you can see it immediately. And just remember that in a closed system, such as in a telescope or a binocular, a terrestrial telescope that has prisms, the first image projected would be upside down. So this would be the incoming image, because as we know, the objective reverses all of the images and flips them wrong side. And that is exactly the purpose of the image correction system, meaning the prisms. So the light goes in here, turns again, another 90 degrees, another 90 degrees, and now the image is flipped, but still looking the wrong side. And now we do the same thing on the horizontal dimension. Poro prisms have what is called total internal reflection. That means that the light is not being corrupted at any stage. What does that mean? It means that in dark prisms, the beam is somewhere along the way split, and then it is being reformed or joined together again, and therefore it needs the special coating on the roof side of the prism. And this is very uncommon. This is the Abe-Koenig prism that you don't see a lot, but it allows to build binoculars with the telescopes a little bit more apart, pointing a little bit more apart, and then creating a little bit nice, little bit of a stereoscopic in fact. And this is today the most common prism. This is the Schmidt dark prism, and this requires not only the phase coating to reconstruct the split beam or the corrupted beam, if you will, but also a dielectric mirror coating. And today these are much more easily produced, much more efficiently and cost efficiently produced. And so most products do utilize most outdoor sport optics products utilize such prisms. And as you can see here, the light beam has a little bit funkier, more convoluted path to the outside. So this much for the typical glass products, which is of course just the tip of the iceberg servicing the simplest of industries. So again, remember, the most important notions and ideas that we have to take home from this are image formation, that is the formation of a viable, seeable, understandable image that one can decipher and make sense of. So this happens by focusing billions of tiny imaginary dots of light and reconstructing to them into a meaningful image. Imagine receiving an assignment of recreating a three-dimensional scene. So the simplest of things you can imagine in front of you, a room with a couple pieces of furniture, a table, a couple chairs, that's it. And then you get a box full of tiny little tiles. It's called mosaic, and they're, let's just say, 1 inch by 1 inch or 1 centimeter by centimeter, and you have to recreate the scene. So this is kind of what happens in optics, and of course that's also something that helps us understand stereoscopic vision, because at a certain point you're going to hit a problem because you won't be able to recreate the image faithfully on a two-dimensional surface from a three-dimensional scene. Of course, light waves from a specific area hit the image forming device. It could be the eye, it could be the medium, a sensor or film in a camera, and the device puts some of the light through to the retina, and an image of the tiny point is formed, and this process repeats itself billions of times until there is a meaningful image. So again, the principles of focusing and image formation, and this is called mapping in optics. So this is what I just told you, the problem with recreating a three-dimensional scene on a two-dimensional scene, and this is also the reason that we have two eyes, and both eyes, each eye is able to perceive a slightly different scene. There is an overlap in the middle, and then we make sense of it in a three-dimensional way. So this much for glass. Now let's take a look at the coatings. The coatings are also the subject of much speculation and lore and all kinds of stories that are not necessarily true. A short history of coatings, how coatings were discovered. They were discovered somewhat by accident.
This Lord Rayleigh went to use one of his telescopes, and when he saw it, he was very upset and dismayed to see that it developed a brown patina on the main lens, on the objective. But he took a look anyway, and to his great surprise, he saw that visibility was improved. He got a better image. So he started trying to figure out what happened. He understood that glass reflects too much light, and therefore it is advisable to develop some sort of coating. Of course, developing the actual glass coating took many years, a couple decades, until it became viable. They first experimented with organic biological coatings, just like they found it originally, which was some sort of growth of a fungus of sort. They tried to make some sort of chemical adherence. That didn't work either. And finally, Smokula was able to produce a coating that was industrially viable. It was possible to manufacture on a large scale, and it was effective. It accomplished what it was supposed to. First, there was single layer coating, and then came multi-layer coatings, which is what we typically use today in this day and age. So there are multiple coatings on each lens. Each lens has its own coatings depending on a requirement. in general terms, coatings can be divided into anti-reflective coatings, which is the main purpose of what we call optical coatings. Then on prisms, you have the phase coating, which helps recreate or rebuild the split beam in certain prisms, in dark prisms. Then there are dielectric mirror coatings, which is also a special coating for the Schmidt prism, which is the most popular or the most widespread today. And there are hydrophobic coatings that repel water from lenses, and that's for outdoor use. This is similar to what some cars have on their windshield, the coating. I think it's called Rain-X, that makes water to concentrate in bigger droplets and run off faster. So kind of like a fancy, good to have feature. Now, optical coatings are extremely thin, about 6 nanometers or less. And of course, it is a difficult and complicated industrial process to make the correct coating. As I mentioned, different instruments, different elements, different groups require different coatings, so it needs to be scheduled and planned out well. Making the coating is still kind of a difficult process, and there's a lot of expertise and experience needed for this. But of course, as the industry advances, so too the younger or the smaller players, the lower quality players, keep kicking the butt of the big dogs. The big dogs who've been in this game for over 100 years, because when they had a, I don't want to say monopoly, but let's just say a firm grip on the high quality manufacturing, it was quasi impossible to compete with them. Now that manufacturing and accessibility to materials, to knowledge, to expertise became so cheap and so easily accessible, it's infinitely easier to make or to produce products that are might not be at that level but approaching that level. So let's just say the lower quality level, the very low quality, let's just say what you would consider almost garbage level. Let's just say not garbage, but the very low level, low quality level today is infinitely more advanced that that same level was, let's just say, 2 decades ago, not to mention 4 decades ago or more. So now you can buy something relatively low price that is being closer to the very high quality. Of course, it's not there. So if you really want the best of the best, you would still have to go with the very expensive big dogs, but it makes it more difficult for them to compete. It makes it more difficult for them to innovate because there's less gains to be made, and there is always more competition. So, as you can see, the industry has its own trials and tribulations. This is what you can see on a cross section and very enlarged, very magnified schematic of the optical coatings. So there's base coatings and a top coat, and like I said, you have the hydrophobic repellent on top, which also has to let through light and not interfere with the light throughput. So this, in a nutshell, pretty much about the coatings. The many layers are because they all do something slightly different. So there are different coatings for different wavelength, for different bands, and all kinds of things of that nature. So it gets pretty precise and pretty complicated. So let's do now a quick recap and remember that the primary take-home concepts are image formation. We just mentioned that. Focus, these two are inherently very closely related. The inverse square law, and actually I want to mention something here. There is something that has nothing to do with the inverse square law per se, but is kind of similar in a funny way in marketing or economics. When you purchase something, there's something that's called the law of diminishing returns. So in other words, the more you spend, the less you get in return. In other words, if you compare a product that costs $2,000 to a product that costs $1,000, you cannot, or typically you don't get twice out of the $2,000 product. You get less. Again, quantify this, especially in optics, is quite challenging. So maybe for someone it is worth double than that. But there's definitely a notion of diminishing returns. You can see it in automobiles, right? It takes you from point A to point B. So if you buy a car for $40,000, it's definitely not going to be twice as good, in quote marks, than a car that cost half that. But again, visual acuity, we spoke about that a little bit previously, and then we also mentioned binocular and stereoscopic vision. Let's talk again about the concept that quantify light in and of itself. The power or the intensity at the source is termed intensity. How the energy of light flows in air, light as energy flows in air, is called flux. It's quantified in lumens. The density on a surface, when it falls, that's what's important for our perspective. That's called the illuminance, how much light falls on a specific surface. And now we have to pay good attention at these last two items, because the difference here is a little bit subtle. So the amount, again, the amount of light that is being reflected is called the excitance. And now the aspect of that reflection, meaning how it is being reflected, the color, the texture, so it's not so much a quantity measurement, but an aspect, the way how it is called luminance. Let's talk about a notion or a designator that is called light throughput. Throughput is sometimes mistaken for transmission. This is not a terrible mistake. No one's going to send you to jail for saying transmission instead of throughput. But in concept, transmission is the transmission or the giving over of movement from one part to a different part, from one item to a different item. So, for example, in an automobile, the movement is being originated in the engine and then it is being transmitted to the wheels. Or you can imagine for yourself an ancient grinding stone that is attached to an animal that walks round and round. If the axle in the middle breaks or someone releases the animal can keep walking, but there is no transmission of movement to the middle axle. Throughput is how much of something is being let through. So, for example, industrial pipes are being specified in throughput. How much of a certain liquid can they put through in a certain amount of time, right? If you put through water, that will flow a certain way. If you put through malted chocolate, that will flow in a different way. So too with light. We measure how much light can an optical instrument let through, or sometimes just a component. And this is how we quantify or specify optical instruments. So what is the throughput? Now, very often we hear that this or that instrument is able to put light through in 90% transmission or 92% transmission. So I think that the optics companies are fibbing a little bit on purpose. They use a term that is yes, better understood by the masses, but also has a little bit of less actual weight, less scientific or technical or even legal weight. So they don't say that the throughput is 92%, but they say that it has 92% transmission. So it might not be such an innocent mistake. But be it as it may, I just want you to know that throughput, the measurement of throughput in spectrometry, is not standardized. It's not standardized anywhere. So anyone can shine a flashlight into their camera lens or the riflescope, what have you, and say that, oh, my instrument has 97% light transmission or whatever. It's not standardized, so no one can put you on the spot. Now, of course, the better companies, the more reputable companies, they do have their own protocols, but of course they don't release them. So they don't tell you exactly how and under what circumstances, what kind of light did they shine into it, what was the surrounding, the ambient light, what wavelength, what intensity, from what angle, and so on and so forth. And all of these things can and do influence the outcome. So when someone tells you that my instrument allows through 92% of light, or 90 or 95, whatever the case may be, take it with a little bit of grain of salt, because whoever told you this is also the one who engineered or planned or scheduled the spectrometry result test. So again, it's not meaningless if it's used by the reputable brands, but it's also not super precise. Let's take a close look at resolution and contrast, because optical device measurement or quality assessment kind of lives and dies by resolution, so to speak. And I will mention to you that in the end, there is no substitute for your testing in real life. So all of the science, everything is nice and beautiful, but you really have to see how the instrument performs in real circumstances. But be it as it may, resolution and contrast are inherently connected to one another. Resolution is the ability to resolve or to discern what we call spatial frequency. So I'm going to show you, but that's what we saw also in the previous video with the line pairs. So the black and white pairs, and as we step back, they seem to melt together. And contrast is the differentiation of color. So color is the ability to discern color. So let's take a little bit of a real life, exaggerated, simulated example. As you can see clockwise from the bottom left, this has very low contrast. The whole thing looks like there is some sort of a coating over it, or you're looking through a screen, something like this. It's very bad. The next one is not as bad. This one is almost good. This one you could call acceptable. This one, I would say that this is the best image of the lot, but some may make the case that this is has more vivid colors, as you can see. And here, this already looks fake. So here they exaggerated the contrast, because in real life you don't see it like that. And also, if you pay attention, if you were actually in person at this scene, you wouldn't see this as black, and you wouldn't see this as such bright white. Why is it? Because the human eye has a greater dynamic range, a greater range of differentiation of small differences in color and brightness. It's mostly brightness than the camera film or sensor. So let's take a look at this image, and here we can understand it a little bit better. So we look at the photograph and we say, wow, this is really beautiful. It's so sharp. It's so amazing. But when you start think about it, when you look at the very bright and very dark spots, you cannot discern a lot of details. So look at the belly of the lizard here. It's gray, and you see a little bit of detail, but not much. In reality, he has much more detail. And if you were actually standing here, you would discern more detail. Same thing, let's just say this very bright spot. This in reality is not so smooth. Or look at the arm. You can see where it's very dark. You do not see those little bumps on his skin. Same thing here where there's a lot of sunlight. Again, it washes out. And where do you have good contrast and consequently good resolution? In the middle, of course, as you would expect. Let's take a look at another example to have a good understanding. So let's take a look. Let's start from the right, because this is how you would properly see it. This is the best simulation of what you would actually see. And this is good contrast and good resolution, or high resolution and contrast. Now, if we go to the image all the way to the left, we see that it's all kind of blended and melted together. Ugh, it doesn't look good. But it does have high resolution, at least in principle. It really doesn't have. But let's just say the mechanical or the software setting is set to high resolution, and the lens did indeed put through a lot of resolution. But we made it low contrast, so the whole thing is kind of blending and melting together and gives kind of a ugh feeling. And this, it looks kind of defocused. It's not focused. It's the same photograph as here, so it's very well focused, and the contrast is good. So the color differentiation is there, but the detail, the line differentiation is not there. So this is what you get. You get kind of an image that's a little bit unclear or unsharp and hazy. And this, in industry jargon or industry parlance, is being quantified by modulation transfer function, MTF. This is a big deal for photographers. And as you would expect, people do make a little bit too much of a big deal. But what it is, it's an attempt at quantifying the performance of a certain instrument. So what we do, we put up certain line pair frequencies at two angles. So we check horizontal and vertical, not really horizontal, vertical. It's called sagittal and meridional. Doesn't really matter. Same idea. So they're a 45-degree angle, and we use charts like this. So as you can see, this is spatial frequency. When there are a low number of line pairs per millimeter, it's very easy to distinguish between them. Then we increase the number again, it becomes more difficult and more difficult. And of course, it is always also a function of distance, because as we walk away from the wall, from the target, these become more and more difficult to distinguish between them. Now, at this point, you would be justified to ask, hey, why are we testing the equipment with such evident shapes, right? These are very sharp edges here, and there's a deep black and a high white. Why don't we make a small detail like we did with the lizard? A good question. In principle, you're right, but it's very difficult to mechanize and quantify it in that way, right? If we would make just abstract shapes, then the whole protocol would be more difficult. So what we do, we keep increasing the spatial frequency, and then that simulates more intricate detail and more blended together colors. And of course, like I said, we also put in the distance factor. But it's true that in principle we should really make a test that is more involved and more detailed. And indeed, in the industry there are more complicated tests. So this is just the simplest of the simplest representation. As you can see, we do check both sagittal and meridional line pairs. We see a denser pattern, 30 line pairs per millimeter, and here 10 line pairs per millimeter, and same thing on the meridional. On this angle, that's again not so important, but if you remember from the first video, when we were looking at the resolution target, then we saw that sometimes the resolution between horizontal and vertical was not identical, even though the shapes were indeed identical and identically spaced. So what we do, it says here it measures contrast. It's kind of true, but it's not so accurate. So this is measuring the throughput of detail of the 10 lines per millimeter, the one that's easier, and this is more geared toward gauging the color differentiation ability or capability of the system, whatever this may be. It will typically be a camera lens, but you could do this with any telescope, binocular, what have you. And then the lower part of the chart, this one shows you the denser, so the 30 lines per millimeter. And again, one of them is for the sagittal and the other one for the meridional. This height denotes a fraction, a percentage. So 1.0 would be 100%. And of course, there is no 100% throughput, because no matter how good the glass is, you can make the best glass in the world, but it will still absorb some of the light. So it's never up here. And even this, I can tell you right away that even if this is the best camera lens in the world, it's very skeptical. It's very doubtful that it would be actually, but 95 maybe yes. Okay, so for the 10 lines per millimeter, okay, that kind of makes sense. But it should be a high quantity camera. But you can see that as soon as it becomes more difficult to resolve, when we look at the 30 lines per millimeter, it plummets to around 80%. And the horizontal direction means the distance from the center of the lens. So the closer for the left hand side, this is the very center of the lens where they tend to perform the best, and this is the very edge. And of course, as a photographer, you want to concentrate on here, not only as a photographer, but as a binocular observer. But if you remember what we mentioned in the first video about fixation, about the area of the light receptive organ in the eye on the retina. So there is a fovea where a lot of light receptors, of mostly daylight receptors, are being concentrated. So typically when we look at something with a binocular, so if you're out on a birding trip, you see a bird, you want to put it in the center. So you put it on a straight line with the sharpest area of vision, the fixating vision, fixating ability of your vision, just like when you're reading a book. So in sport optics, really this is more significant, but photographs, they are spread around a larger area around the entire sensor. So there might be something interesting on the very edges of the photograph or even on the inner third that is far from the center. Again, in a lot of binocular applications, you're hunting, you want to age and sex the animal. So you would, of course, use mostly, for the most part, almost only the very center of the lens. So this is a good indicator for you. But of course, you also want to be aware of peripheral vision, so you shouldn't ignore that either. And if you remember, we also mentioned that the limit of human visual acuity was 1 minute of angle, 1/60th of one angle. Remember that? We called it 1 MOA, which means that if we look at something that creates a 1/60th of an angle of a good resolution, like on this chart, so a black square on a white background or vice versa, it's a little bit more accurate to say a white square on a black background if we're trying to gauge or if we're trying to stimulate a single light receptor. But again, that doesn't really belong so much here. But the main idea is that the limit of human visual acuity is at 1 MOA, 1 minute of angle, and this is how it would look in real light. In real life, I'm sorry. You have here an object that is 1 inch, and it is 100 yards away from us. Of course, this is simulated. Then it would create an angle that is 1/60th of 1 degree. And it would create the same angle if we would enlarge the target to 2 inches and push it out to 200 yards. And same thing, 3 inches at 300 yards, 4 inches at 400 yards. And again, this is just a mere coincidence that this is 1/60th of 1 degree, and dividing the circle into 360 slices is also probably arbitrary. It's not based on any kind of natural phenomenon or logic. There is another system that divides the angles differently, but what I'm trying to point out is that the science of triangulation is also based on this idea. So if we know the size of this target and we know this angle, we can use the law of sines to find out this side of the triangle. So we're trying to build a big triangle between the eye and the size, the height of the target, and then back to the eye, and we can divide it in two to make two straight triangles and use the law of sines. Now, of course, I can already hear some of you scream from the back, what are you talking about? We need one more constant in order to use the law of sines. Yes, you are right, but once we find one solution for this problem, we can then convert the solution into a constant, a multiplier. So once we found the answer, we turn it into a ratio, and that is a multiplier. So this creates a super simple formula. We divide the size of the target in inches by the size of the target in minutes of angle, multiply it by roughly 100, and we find the range. This is how it works. So this is 2 divided by 2 MOA equals times 100 equals 200 yards. Super, super simple. And this is what I mentioned to you. This is the other system. This is called the radian system. Again, a little bit off topic here, but since I brought it up, I will talk about it. A radian is taking one radius of the circle and putting it, here on the circumference. And then once I'm at the end of this distance, I go back with the radius. And this is kind of a bigger pizza pie. It's a pizza divided by roughly 6 instead of 8. And this creates a radian. We divide this by 1,000, we get a milliradian. And some people use MOAs, some people use milliradians. By the way, none of them have anything to do with either the metric or the imperial system. It simply just so happens that a lot of people who prefer using the decimal system because it's simpler, they also prefer using radians, and it's kind of like a military thing. And a lot of people who think in imperial measurements prefer to go with MOAs, but none of them is inherently dependent on or tied to either the imperial or the decimal system. Let's take a very practical use of this formula just to show you. So you want to know how far this deer is away from you. And by the way, this is not a shooter. I would say in most states, in most seasons, this would not be a shooter. But anyway, what you want to measure is from the top of the back to the brisket. So roughly this measurement. And let's just say that this riflescope puts an interval of 2 minutes between each line. It's usually more, but let's just work with 2. It's going to be easier. So, of course, it has to be a constant. So you have to know, you have to be able to gauge. So a deer about this age and size, I would say, is somewhere between 12 or 11 inches from this part of the back to the brisket. So that would be, in real life, if you would measure the deer himself, that would be 11 inches. Now let's count MOAs. So we'll start from here and we go 2, 4, 6, 8, 10, 12, 14, 16. And we're going to take out our calculator. We said, what was the formula again? We said size of the target in inches. So we said that this was 11, right? Divided by 16 MOA, we get roughly 3/4 or about 70%. So let's make it 0.7 times 100, 70 yards, a little bit less than 70 yards. So we know that this deer is roughly 65 to 70 yards away from us. And if someone would decide to take a shot at it, they would make an adjustment based on where the rifle is adjusted. And this is just what this method or this discipline is, triangulation. Today, this is considered super primitive because we have much, much more advanced instrumentation. Many of them are also optical or optoelectronic. If you ever seen engineers, civil engineers on the road, they use a little device on a tripod that looks like a box. So that's kind of a telescope with a reticle. And again, today it's all laser based and it shows elevation and orientation and things of that nature. So very advanced. Let's take a look at what the industry throws at you. So these are the optical terms that pertain to optical instruments. First and foremost, focal length. This is super, super important in any optical instrument, any optical system. Of course, in terms of consumers and marketing, it is more relevant to photography. In binoculars, we don't talk so much on focal length, but a lot of telescopes, especially astronomy telescope, talk about focal length because the magnification of a system like a telescope-based system, like a binocular or any kind of telescope, is dividing the objective's focal length by the eyepiece's focal length. And in variable systems, right, like a lot of spotting scopes or riflescopes, where you can change the power. When I say power, I mean magnification, not optical power, of course. I should have mentioned that in optics, when we say power, that is the bending power, refracting power of a lens, which has nothing to do inherently with either focal length or with magnification. Of course, you build on that, but there are two different terms. So sorry, I should have mentioned that earlier. But be it as it may, when we change the focal length, when we vary the distance between two lenses in the eyepiece, we decrease, in order to go up in magnification, we decrease the focal length of the eyepiece. And so when we divide the focal length of the objective by a smaller number, we get a greater magnification. And of course, that comes at the price of quality. But again, today, most variable eyepiece systems have caught up with their non-variable counterparts for the most part. Entrance pupil, super, super important. Actually, this is even more important than the focal length. I should have put it first. The entrance pupil is, in rough terms, the opening that lets in light. So the primary aperture. This is not to be confused with the diaphragm in a camera lens that is used to restrict light for photographers. So photographers call it colloquially in their jargon aperture, but here it means the primary opening to let in light. Now, entrance pupil and objective lens diameter are not 100% synonymous. For all intents and purposes, from a practical perspective, they are the same. But in the commerce today, what an optical brand will give you the objective diameter. And if they are truly honest, and today this is much less of a problem that it used to be in the past, this would actually refer to the diameter that's visible, that's available to let light through. If you think about it, that lens or that objective system have to be caught or have to be suspended somehow in the instrument, so that takes up some space. So it's not truly the physical measurement of the lens edge to edge, but how much light it lets in. And the entrance pupil is really a fictitious, not really a fictitious, but it's not a real measurement. It's not a physical measurement. It's the measurement of the image of the first restriction of the aperture. So for all intents and purposes, it is the aperture, and in common parlance, you can also call it the objective lens diameter. It's a virtual image that you could theoretically project in front of an instrument, and in most instruments, in other words, pretty much everything other than camera lenses, that would be very close to the outer element of the objective. So right in front of the last part, of the outermost part of a binocular, for example. Now in a camera, you would restrict the aperture. So if you restrict the aperture, then the entrance pupil would be further out, kind of outside of the system. But again, right now, it's not really relevant and not really practical. But this is super important because determines how much light can theoretically enter the system. That it's the upper limit of the light allowance of a system. No, not more light. More light cannot enter the system than the entrance pupil. Let's put it this way. So the entrance pupil limits how much light can enter the system in one time. The exit pupil is what comes out. So for example, if you shine a light into a telescope and it's assembled and you have an eyepiece, then the light that comes out of the eyepiece, the diameter, is called the exit pupil. And that is important because you want the exit pupil to at least cover your pupil. Otherwise, you will have a black border around your field of vision, and that is very uncomfortable and very disturbing. And some people call exit pupil beyond the size of the pupil wasted light, which in absolute terms may be right, but really you need that because there is tremor, your hands move, your head moves, so you want actually the exit pupil to be larger than your pupil when you're viewing. So if you usually view during broad daylight, it's not such a big deal, and you get the size of the exit pupil by dividing the magnification dividing the objective lens diameter by the magnification, and that will give you the exit pupil. And you want to make sure that typically it's at least 5 millimeters which is a dilated human pupil. The exit pupil distance is what's colloquially known as eye relief. It is simply the distance at which you can comfortably put your eye and get a good optimal image. This is typically a range, and depending on the instrument, sometimes you have to be fairly precise, and sometimes there is a good allowance, good tolerance for placement of the eye, meaning the head. That's fairly typical of riflescopes. Some good quality astronomy telescopes will have a good tolerance, good allowance for movement behind the eyepiece, but typically it's relatively restricted. You have a couple millimeters. Angle of view or field of view is the amount of lateral field that is visible in front of the viewer with an instrument. And it can be expressed either in an angle, such as 7 degrees, 8 degrees, and so on and so forth. Of course, in camera lenses, the actual practical effect or outcome of the focal length is a certain angle of view. So a camera lens with a long focal length, let's just say 150 or 200 millimeter focal length, will show you a smaller cut. So let's just say at 100 yards distance from you, it will only show you a distance of, let's just say 5 yards lateral. Whereas a wider lens, that's why they also called narrow and wide, let's just say a 35 millimeter at a distance of 100 yards for you, will show you a much wider field, 50 or 60 yards, something like that. I don't remember offhand. And same thing with telescopes and binoculars. So it's a big deal. Usually, the more field of view, the more desirable it is, and of course, the more magnification, the smaller or the narrower the angle or the field of view. Depth of field is a similar concept, but it focuses on focus. It means how much of the scene before us on the z coordinate. So we talk about the x coordinate as the vertical line of a chart, and the y coordinate is the horizontal, and the one that's between you and your conversant or you and your target subject, whatever it is, that's called the z coordinate. And how much of that field can be in focus is called the depth of field. And typically we want a deeper depth of field. Of course, it's being limited by numerous factors. The magnification is a prime limiting factor, so is the aperture. And of course, in photography, it's kind of a big deal. And in photography, sometimes a shallow depth of field is desirable. In most optics, typically we want a deep depth of field so that we don't have to always use the focus to focus back and forth. Twilight factor is a formula that attempts to gauge the performance, especially the low light performance of an instrument. But in reality, we should not pay any attention to it because it's really not useful. Primarily because the only thing that it takes into consideration are numbers. It takes in consideration the objective and the magnification. And what it does, it takes the square root of the objective multiplied by the magnification, which, if you haven't realized yet, is totally meaningless. So it doesn't address the quality of the glass and anything else. It just works off of numbers. But anyway, I'm going to come back on that in a little while. And stereo base is a little bit less relevant to us, but that gauges or that determines how much of a stereoscopic vision we can have, typically with a binocular, and that is a function of the distance between the objectives and the magnification. The inner pupillary distance is the distance between two eyes, again, mostly relevant for binoculars. So now let's take a look on what's on the instrument itself. We have the objective instrument. We often call it an objective lens, but it's really an objective system. And it's within the front housing. And in many systems, it can be its own thing. So a camera lens, it's just an objective system. An OTA in an astronomy telescope, that's mostly just an objective system. But in a closed system, for example, a riflescope or a binocular, the objective is the front part of the product. So the one that's further away from the viewer. Next up, if necessary, if the system calls for it, there needs to be an image correction or inversion system, which is typically prisms, although sometimes they could be mirrors. In war times, there were binoculars and spotting scopes made with mirror-based inversion system instead of prisms. Then again, in many systems, there will be an eyepiece. In a camera, for example, there's no eyepiece. The camera itself is, in some ways, fulfills the role of the eyepiece, if you will. But in many in direct viewing instruments like telescopes and such, there is an eyepiece. It can be an integral part or a separate parts. Inside of the system, it talks about different elements in groups. So the elements are lenses, and the lenses can be cemented or they can be air spaced, and how they are being grouped are grouped. Again, this is mostly a big deal for photographers. The mount, that how the system is being mounted. So for example, most practically, a camera lens would have a mount to mount it on a camera. That could be a screw mount. That could be, today there are mostly bayonet mounts, and each brand has its own system. So that they shouldn't be compatible with another brand, they kind of try to force you in staying with them. There is a focusing mechanism in almost all optics. And then, of course, there could be other mechanisms, such as the adjustment system in a riflescope, the variable eyepiece system, the hinge on a binocular, things of that nature. So what's really, really very important to remember is not to rely on hype and not to rely on numbers alone, but we have to check the quality. And in general terms, any optical product, maybe not only optical, but definitely optical products, have to be gauged and have to be tested or evaluated for the three Qs, the three main components: quality, quality, and again, quality. That means optical quality, mechanical quality, and structural quality. And we want to stay away from marketing hype and all kinds of buzzwords and terms that are interesting. Really, what counts is the actual performance of the instrument in real life. One, two, three. So how do we do this in real life when we know that it's very difficult to know what is actually true and how to gauge this? Unfortunately, for a normal, regular consumer who doesn't have access to a lot of different products like this, there is not much else to do than to rely on information from the internet. So today, we are blessed that there is so much proliferation of information, and a lot of it, the information is good, but unfortunately, a lot of the so-called information is horrible. So we need to know how to weed out the bad from the good, or maybe conversely, the good from the bad. And I gave you a good starting point, so now you have a much deeper understanding. But understand that all of these products, they are being sold and marketed almost entirely based on specifications that are just numbers. They don't really mean anything. They do have a concrete physical meaning. For example, camera lenses are being sold as X focal length slash X aperture, so maximum aperture. But they're just two numbers that pretty much only tell you approximately the angle of view of the image that you can take with it and the largest aperture that you can open. But it doesn't really tell you the actual quality of that lens, the sharpness, how it renders color, and anything like that. So if you cannot go to the store and take a bunch of photos and compare them, obviously you have to rely on friends and family, fellow photographers. Same thing with binoculars, right? Binoculars are being sold with two numbers. The second number is the objective lens, and in many optics like this, so terrestrial telescopes, meaning spotting scopes, same thing with riflescopes, same thing with binoculars. Astronomy telescopes are sold a little bit differently depending on the technology that they are being made of, because they can be of varying technologies. But the basic idea is the same. They throw you a couple numbers. They tell you that this is a 1042 binocular or an 842 or a 1032. The second number is the size of the objective lens. Hopefully it's the actual aperture, and that's the diameter given in millimeters. And the first number is the magnification or power, how much time it enlarges the image in front of you. And in direct viewing optics like binoculars, it's very easy to gauge. It just compares what you see through the binocular to what you would have seen without the binocular. So you see something in front of you, and the binocular will enlarge its appearance by 10 times, or you will get 10 times closer. You will have the feeling or the illusion of being 10 times closer than you actually are. With camera lenses, it's a little bit different, but it's the same idea. It just gives you two numbers that are no testimony of the actual system's quality. So you need to be able to gauge that. And by the way, with the sport optics, there's no such thing as 8 by 42. You don't multiply. It's not a elementary school exercise. It's a 32 millimeter binocular with 8 power or 10 power or such. So another thing also, sometimes we have to take into consideration not just the actual numbers that are being given. So for example, you're considering two binoculars, a 32 millimeter versus a 42 millimeter. So the 32 has the advantage of being a little bit smaller, a little bit lighter. Conversely, the 42, in exchange to a couple more dollars and a little bit more weight and a few more inches, you will get more light ingest. It will let more light in, which will result in a brighter image, sometimes better resolution, better contrast, as we spoke, a nicer image. But how much? So if you just go by 42 versus 32, that's roughly a 35% increase or so, which is considerable also. But what we need to do is need to calculate the surface area. So how do we do that? We do the radius squared times pi. So we will just approximate this, but 21 squared times 314 comes up roughly to 1380. Okay, I rounded it a little bit down. And then if you do the same thing with the 32, this was the 42 millimeter binocular. If we do this with a 32 millimeter binocular, so we take the radius, which is 16, square it, multiply it by 3, we get 800 roughly, a little bit more than 800. So now 805 versus 1380, that's a more than 70% increase. That's gigantic. So you have to think about it in this term. Now, the flip side of this argument is that in recent times, the price difference between such products is relatively small. So until, let's just say, 20 years ago or so, the price between the same or similar binocular, it's not really the same, but a binocular with the same brand and the same product line, so meaning the same quality level, a 42 millimeter would have cost us considerably more than a 32 millimeter, right? Now the gap is being closed again because we pay more for labor and services than for materials. So just because the binocular is a little bit bigger, that doesn't add so much to the price. So the gap is being closed. So that's something to think about. Again, just read what you see on the slide. This is what we need to concentrate on. All of the actual performance of the product, the ergonomics, the weather resistance performance. There is something that's called the ingest protection standard. So it's a rating. If you see some products, you will see that it says something like IP67 or IP65 or 66, something like this. So IP means inches protection, and the first digit means for solid, and the second digit means liquid. Very often, if the product is protected from liquids, then it goes without saying that solids cannot come into the system. Solids are more for things that have openings and grills, like I don't know what example to think about. Maybe an AC condenser unit that stands outside. So that would be an inches protection only with the first digit, right? How big is the maximum size particle that's allowed or that's capable to enter the system. Same thing with closed systems like flashlights and optical instruments that are meant to be waterproofed or water protected. So the second digit is the one that is meaningful, and I think the highest is 7 or 8. So 8 means that it can completely be submerged to X amount of pressure. I forgot how much, but it's a good amount of pressure. So it can fall into a pond that's a good couple feet deep and stay there for a couple of days. That's the highest rating. That's typically things that are meant to be submerged. And I think 7 is the next step down. That's something that can occasionally be dropped, and so on and so forth. So the lower the digit, the lower the protection from ingest of liquid. Let's also talk about something that used to be a big deal, and thank God, the openness and the availability of information on the internet mostly killed these bad notions and bad ideas. One is an RBI, which is called the Relative Brightness Index, that is total nonsense, meaningless. These indices are at best just gimmicks, but the RBI is totally useless. All the RBI does is it takes the result, the exit pupil. So it divides the objective lens diameter by the diameter by the magnification. We get the exit pupil and then we square it. It means nothing. It didn't give us anything. This is somehow supposed to gauge something, but we don't know anything about the quality of the instrument, how well the glass is done, how well it's been designed or engineered, and so on and so forth. So this is just plugging a number and playing with it. It's like I could tell you, if you stick your paycheck and you divide it and you multiply it and you square it, then ABC. Bottom line, you're not going to have a penny more in your bank account, so it's meaningless. The second one, the twilight factor, is also mostly nonsense, but at least it has some sort of logic to it. So the twilight factor supposedly gives you some sort of idea of the performance or maybe the low light performance of an instrument. What it does, it multiplies the magnification with the objective and then takes the square root of that, and it gives you an index, so-called. But again, this is also pretty meaningless for the same reason. It doesn't take into consideration the quality, the optical quality, so there's no throughput, no resolution, nothing taken into consideration. A $50 piece of junk will give you the same twilight factor than a $5,000 masterpiece of optical feat or optical engineering. So that already should put a big X on it. But let me show you how even the numbers don't really make sense. Take a 750 binocular. Those of you who know, this is typically a marine binocular. It's not for high detail. It's for scanning big swaths, big distances. Sometimes some birders like to use it in dense areas under the canopy of a forest for birds that they not going to see from not very long distances. But anyway, this is a lot of light binocular, 50 millimeter objective with only 7 power, 7 times magnification, is considered a relatively low power binocular with a relatively big objective lens. So it lets in a lot of light and it has a nice, big, beautiful picture. It's easy to hold it. You don't see the shake and the tremor so much. Compare that to a hypothetical pocket binocular that has a 25 millimeter objective and 14 times magnification. Okay, thank God those crazy stuff, crazy ideas are not being sold or marketed anymore that much, but it's not excluded that someone would sell a binocular like this, a 1425 binocular, which is insane. It's impractical. But let's just say, so 7 times 50, 350. 14 times 25, the same, 350. Square root is roughly 18 and some change. They have the same twilight factor. So throw it out of the window. This is just plain stupidity. And same with any kind of marketing gimmicks and buzzwords, all kind of ideas that they give you. They very often the industry now is trying to shave size and weight, so they come up with all kind of interesting ideas. One is newer alloys. So if you alloy aluminum with scandium, then it reduces the specific weight of aluminum. So they send you a scandium body, a scandium body. How much scandium is in it? Between 1/10 and 1/2%. So they alloy the aluminum with a little bit of scandium and it reduces the specific weight. But it's not a magic alloy. Today, the scandium alloy or scandium aluminum alloy is strong enough, even to the extent that you can manufacture firearms with it, again with limitations, but it's not impossible. So it's robust enough, but the saving is not that big. It's mostly hype. So you have to be able to gauge that and understand the numbers. Now, what would a normal person who doesn't have access to testing, you have to rely on other people's testing, unfortunately. But this can show you, if a few friends come together and they can do a product testing, or let's just say you have a demo at a trade show, or even you can see a lot of people do these videos on YouTube. Many of them are reliable, at least to some extent, but this will give you the general idea on how to do this. So let's just stay with binoculars because it's pretty simple, but the idea is the same with camera lenses, riflescopes, spotting scopes, telescopes, what have. Well, astronomy telescopes is a little bit trickier, but what you can do is you set up a target. You rip out a couple pages from some magazine and you hang them up on the tree trunk, and then you take several binoculars, several instruments that you want to test, that you want to pit against each other. So the test has to be meaningful. And what you want to do, you want to compare instruments that are as similar to one another as possible. And then you isolate hopefully one variable, one component, one aspect that you want to test or evaluate. So let's just say that you think that you want to get a 1042 binocular, which is for many years that was the almost the default binocular for hunters and for many birders as well. But let's just stay now with this spec. So you want to compare 3 brands of 1042s. You want to set them up and you want to make sure that they're in the same quality range, same price range. So brand A, brand B, brand C. Don't just go by top of the line, but see really the reputation of the brands. The brands themselves have to be kind of in the same quality family or reputation family, and then the products also in the same price and purported or advertised quality level. And then you set them up on tripods and you look at the same targets. You look binocular A, what was it able to resolve on the page of the magazine? The big headlines, the secondary headlines, the paragraphs. Can you read words? If you go to a different distance, how does it behave? Write it down, compare notes. Go from a shaded area to a sunny area, from a sunny area to a shaded area. If you can do it at sunrise, sunset, under rainy or at least cloudy conditions, and so on and so forth. Or you want to evaluate the effect of the size of the objective or the magnification. So you isolate that detail. Okay, so you want to see how an 842 performs versus versus a 1042, for example. So don't compare an 842 to a 1032. Compare an 842 to a 1042, preferably from the same brand and the same product line, or compare a 1032 to a 1042, and so on and so forth. So isolate one aspect, one detail, and try testing it. And as you can see, it's not very easy, not very convenient. If you're into it, that can be very interesting. Make sure to take notes because typically you won't have another chance to do it. So take as many notes, as many photographs and as many impressions as you can, and write it down as soon as possible, hopefully or preferably on the spot. So I think that we covered quite a lot of ground, and that after this, you will be ready to go into individual instruments. Let's do a quick recap. So it's right here on the slide. Of course, glass is the main component of optics, typically made of lenses. The objective lens is the first and the biggest, and in some ways, the most important component in the system. Let's just say the big terms that we need to concentrate on is image formation, focus, resolution, depth of field. Okay, parallax is more for rifle shooters and photographers. Depth perception doesn't really belong here. Magnification. A prism is an inversion, part of an inversion system, and simple optical instruments are very purpose or use specific. Again, designing the instruments, there's a ton that go in it. It's not just an optical engineer. Again, if you would leave the whole process to the optical engineer, who would come up with a monstrosity, a huge hunk of glass that would be very impractical, even though it would be an optical miracle. And same thing, if you would leave it to the director of sales, he would tell you a story that this is a Rolls Royce and a yacht and a private jet all combined in one, and so on and so forth. If you would leave it to the accounting guy, he would give you a piece of toilet paper and charge $5,000 for it. So that's why it has to be a sum of all of its components. It has to be good and viable and marketable. And there we go. A little bit of the concept of image formation. Remember that when you look through a direct viewing optic, you're not really looking at the target, but you're looking at the virtual image that the eyepiece gives you, and it is projected forward sort of towards the instrument, towards the target. And like I said here, again, all of the simple optical instruments are unique to their own purpose. And so I wanted to thank you very, very, very much for taking this journey with me. And I hope to see you soon in the specific videos. I don't know in what order they will be released and recorded, but we will do it just like we did the introduction. So we will talk about camera lenses and riflescopes and binoculars, what have you. So again, thank you very much and good viewing.